Right. So welcome everyone. Today we got Xiangyu Zhang from the University of Minnesota. He's a fourth-year PhD student working with Sarah. I noticed that Sarah is here. And he's been working with us for a few years now on this a new kind of method to model differences between a source spectrum and a background. Well, source anything and a background as long as there's some discrimination. So he's going to tell us something about how exactly it all works. So Xiangyu, take it away.
Yeah, thank you for introducing this. Today the talk will focus on the smooth test of goodness of fit for the astrophysical searches under the high background. This work is collaborate with Sarah, Winnie, Margarita, and Charlie, where Sarah and Charlie are my advisors, and Winnie and Margarita are our great collaborators in astrophysics. Okay, so let's get started. So first, we will introduce the goodness of fit test problems because the smooth tests, after all, they are a solution for the goodness of fit problems. And the setting here is that we consider X to be a random variable X to be a continuous random variable with support curly X, that is a subset of R1. It has some unknown distribution, upper P, and density small p. And the goodness of fit problem here aim to assess whether or not our P belong to a specified continuous distribution function, J beta, with density small j beta, and this beta is belong to some parameter space upper B, and it's a subset of Rp. And beta here can be known or unknown. Formally, this corresponds to our test of hypothesis that P equal to J beta for some beta versus alternative that P not equal to J beta for all the betas. And the smooth test also have some solutions for the goodness of fit problems when X is also discrete, or your curly X, your support X is a subset of RD. But to reduce the technicality of this talk, we will not focus on them today. And if you have some problems, maybe in these settings, maybe we can talk afterwards. Okay. Then to introduce a smooth test, we need to first give a background introduction of the orthogonal expansions of the density ratio. Okay, so here under some regular conditions about the density ratio P over J beta, that's the stuff that we want to expand under some this technical conditions. It can be expanded via a series of orthonormal basis functions per set J. Okay, so here the orthonormal basis functions will require it to be square integrable with respect to this unit interval 0, 1 with respect to the measure J beta. So here for convention, we always let the per set 0 to be equivalent to 1. So that our expansion here start with theta 0 beta. Actually, it is theta 0 beta times 1, but we always set per set 0 to be 1. Okay, and here this is our expansions. Here, of course, you can write your expansions that like per set J of X. Okay, but here we write it as a G beta X because we do not want to every time we change the support, maybe we change to different frequency beams we are focusing on, we do not want to change our orthonormal basis functions. So that we add a instead this is called a probability integral transform to it, so that your orthonormal basis functions is always between 0 and 1. Okay. And to make this density ratio, this expansion integration to 1, we always set this theta 0 beta equal to 1, and we let the composite of per set J and J beta denoted as Hj beta X. Okay, and here this is our final expansions look like. And of course, we know that the coefficient theta j beta here is the inner product between this density ratio and this Hj beta X, and our inner product is with respect to the measure J beta X. So this is our inner product. What the coefficient will look like. And if we can cancel out, if we cancel out this J beta and this DJ beta here, this is what we will get. Of course, here, since P is what we are trying to test, this is unknown. So indeed, this theta J beta hat here is unknown. And but if we can get collected data, okay, about your distribution P or your random variable X, you can replace this upper Px with some empirical distribution function Pnx so that you have an estimate of this parameter theta J beta. We will see this in a minute, but that's the idea. But by the way, if you have any questions, you can stop me anytime you want. Okay.
I have a quick question, Xiangyu.
Sure.
So, can you give us some motivation as to why this is useful to do? I mean, what is it that we would gain by doing this sort of thing?
Right. You will see this actually in the next slide. But this is a very good question. Let's say the next slide and see if it can answer your questions. Okay.
Okay. Sure.
By the way, yeah, another thing about this autonomous basis functions is that maybe it can be some shifted Legendre polynomials that we focus on, or some cosine basis. Okay. Let's see the next page. Okay. Here we consider the smooth model. The definition of the smooth model, it tells us like that when we consider the PMX, this is what we call the smooth model, it's equal to our postulated or null model J beta X times the expansion. But this expansion is gets truncated at the point M here. So it gets truncated at this point M. Okay. Why we want to do this? Okay, why we need this smooth model? Because you can consider this smooth model as a generalization of the true density. When M goes to infinity, you get your true model, right? You get your true model Px, but if you truncate it at a point M, you get what we call a smooth model. And by the smooth model, we can have the test that if we want to test the smooth model of whether or not Pmx equal to J beta x, what we are trying to test is all of these coefficients, where all of these coefficients, whether or not all of these coefficients equal to 0 versus the alternative that at least one of these coefficients not equal to 0. And then we can consider, and this is commonly referred to as the smooth test. So we can consider this smooth test as a generalization of our goodness of fit test, because when your M goes to infinity, you have your test become Px equal to J beta x, or all of these coefficients, infinite of these coefficients being 0 or not, right? It becomes your original goodness of fit test. But here we consider a truncation to it, and we want it called a smooth test. Why we need that? Because if we really test every directions of the deviations from J beta x, if we test so many of thetas, we will lose a lot of power, because you cannot get a very perfect test that you have a very high power for each of these so many directions. So the idea of the smooth test is that, okay, we take some compromise. We reduce the directions of the alternatives that we focus on. We only focus on that much of the directions of the alternatives. That direction is spanned by the all of these autonomous basis functions Hj beta. And the smooth test indeed concentrates the powers towards this finite number of possible directions specified by this autonomous basis functions H1 beta up to Hm beta. Okay, so indeed that's why we need that expansion. So we want a truncation, and then we postulate our smooth test because of this. And for the power, of course, it depends on your selection of your M and how you choose your autonomous basis functions. I saw somebody have questions. It's Jeff. Sorry, you have a question?
Yes, I apologize. I came in a little bit late, and maybe you already discussed this, but to to me, smoothing is sort of a bad thing in general, because smoothing discards information. I mean, that's just a sort of general
Right.
point of view. What is the motivation here for smoothing at all?
Right, that's a very good question. So, indeed, if we want to consider the original smooth test here, okay, for the traditional Gaussian sulfate tests, okay, we have some Kolmogorov-Smirnov tests, some Anderson-Darling test basic. That's a thing that.
Okay, can I jump in for a moment, Xiangyu?
Sure. Sure.
What Jeff, I believe, is asking about is smoothing itself, as
Right.
not smooth tests.
Yes, exactly. And one way of saying it is that sometimes smooth data are a sufficient statistic, but often not. The smoothing discards information, and so it's if there's a way around it and doing a non-smooth analysis of the same kind, it's better. So.
Right. So yeah, to answer your question, it's indeed, of course, we will discard some informations, right? But think of it in this way: if your true model is really something that is your postulated model times some expansion like this, and if you try to test the area of its directions goes to infinity, then you will lose some power towards other directions. And now if you can only focus on this part of the deviations, you will focus your power on these directions so that you will get higher power. So that's the idea. Does this answer your question? So indeed, we don't know what is the true model is, but if I know maybe astrophysicists, they have better sense of modeling the world. They have some idea of this how, if your model gets rejected, how the true model will look like. They will think maybe this is useful.
So do I understand what you're saying is that when you talk about smoothing it here, you're really referring to the model and not something that's done to the data ahead of time. Is that correct?
Correct. So far we don't talk about data, so it's
okay.
Only
fine. No, again, I apologize. And
yeah, sure. No, any other?
Just to make sure, people who are not statisticians see the point of what you're doing. Vinay was asking, maybe you want to bring an example of what your P and your G beta could be for astronomers, for instance.
What do you mean? You mean the example that we do with Winnie or some other example?
Like, the motivation, right? So you're talking about in your title about modeling high background. So what do these P and G beta refer to in that setting?
Oh, right. Okay, that's great. So G beta can be for example, your data can be the background data, okay, background only data, and your G beta X can be your background model. So maybe you are experiencing some high background and you have some original of your background. So you are not sure whether or not you try to update your background or not. And maybe if you don't know your background, okay, this G beta X can be a uniform, but if you know some previous background, you can set your G beta X to be your previous background. And when you get new data, new background data, you are thinking, okay, maybe I'm experiencing some new background, and I maybe need to update my background model. And here it provides you a way. You can think of it provides you a way to update your background distribution, background density, and here is how to do the test update it. Okay.
Can I interrupt and sort of put it in terms that perhaps it'll be more familiar to astronomers like Jeff? So let's say, Jeff, so consider an example where you might have a spectrum, and you're trying to find a little feature in the spectrum. You believe you know what the background is, and let's say that is G beta, and you're testing whether, and you can test quickly whether this G beta is a good representation of the data. And if it is not, then there is a simple way, it's almost parametric, well, not almost, which is, sort of a non-parametric, parameterized way of looking for deviations from this background G beta when you're looking at the actual data to see if there is something, if there's a feature that shows up. Xiangyu, Sarah, correct me if I completely botched the explanation.
Technically, it's semi-parametric. So, Xiangyu, can you go to slide 3, maybe? Yeah, so the idea is, okay, so suppose P is your unknown background distribution. G beta is some guess you may have for it. If you're looking for spectral line, maybe your GB is uniform, as Binay was saying. And the trick is, instead of modeling P directly, we're using kernel density estimation or things like that. We model the ratio between G, your postulated model for the background, and the truth, so that if your postulated model is already good enough, you don't have to update it at all. If it is not good enough, Xiangyu, can you go to slide 4? If it is not good enough, then the thing that Xiangyu has in equation 4, blue bracket, gives you an update for it that will be estimated using the data. So
Thank you.
it's basically a Fourier expansion for the density ratio instead of for modeling the whole background.
Yes, thanks for the explanation. Yeah, indeed, that's what we will talk in the next slide. So that's one of the features of the smooth test. When your null hypothesis or null model G beta X get rejected, the smooth model or the smooth test provides a natural way for you to perform a corrections for your postulated model that get rejected. And this correction in statistics is called the smooth estimator, and it is defined exactly as what we see in the last equation, but the estimators here get estimated, right? So previously we mentioned that this theta J beta is unknown because it is the inner product. It's this equation, but with a dpx, right? And P is our unknown distribution function. And when your data gets, when you collect your data, of course, you can replace this px distribution function as an estimate of the distribution function. It's called the empirical distribution functions, and it uses your data exactly. Okay, so that you can estimate your parameters theta hat j beta, and it equal to, and it indeed equal to this. Okay, so that's the intuition is that when you're testing some model, okay, and you get some data, you test some model, and if your model unfortunately get rejected, you will have a way for naturally correcting it, and the smooth estimator provides such a way for you to correct it. Okay, and of course here the corrections also depends on how you select your basis functions and how you choose this M. Okay, so yes, and here when we're talking about a test, a smooth test, of course we need to talk about its test statistics. And here, assuming that M is given, okay, order M is given and the beta is known, the test statistics that can be written is written as this way. Okay, so here it's a summation of your theta hat squares times n. And to provide you some intuitions about this theta hat square is if this theta hat, the magnitude of theta hat gets larger and larger, your model, your null model J beta X will be more and more different than your smooth model, right? So that you are prone to reject the null hypothesis. So that when SM is larger and larger, you will prone to get rejected. So that's the intuition of this test statistics. And we know that under the null, and as n goes to infinity, this convert to a chi-square distribution because this is simply application of the central limit theory. Yes, I saw Tenweir, you have a question?
Yes, I have a quick question regarding equation 7. So from what I understood, h is like your basis function. So I'm wondering, like, since you're just taking an average on basis function, like where is actually data coming in to give you the estimation? Like the way it's written, it simply looks like, right, 1 over n summed over like basis function that you are already
Here is
like,
our data. Xi is our data.
oh, okay, I see. Okay,
Yeah,
thank you.
sorry, that's not very clear. Yeah, Xi is the data. Sorry about it. Yeah, yeah. Yeah, I should say that the small xi's are the observations of the random variable upper x. Okay, so yeah, small xi are our data. Yes. If there is no other question, I will go to next sequence. Okay, so after we see the previous methodologies, it can indeed already be enough for us to solve some real data problems. And the real data problems here we are focusing on is about the RT-crew. So this is a symbiotic system. It's a high-mass white-dwarf accretes from the one of M53 right giant companion. And the RT-crew actually exhibit some variability features like the aperiodic flickering and strong correlations of spectral intensity with the overall brightness. And our question is, what is the origin of these variabilities could be? Okay, and to answer these questions, based on the observed X-ray spectrum produced by RT-crew, the origin can be modeled as either the intrinsic change in the soft thermal emission component. Okay, so that's one potential sources. Another is changes in the continuum component due to the intervening absorptions. And the presence of the spectral lines during the increase of soft flux would support that it is indeed originate from the intrinsic change in the soft thermal emission, and while the lack of such lines would favor the latter scenario.
Xiangyu, may I make just a quick comment? For people who are not familiar with what we mean by a soft component, right, is below 3 kiloelectron volt, 0.5 for Chandra, right? Soft or to 1 kiloelectron volt. That's what the soft flux here. Thank you. Just clarification.
Yes, thank you for your clarification. It's very useful. Yes. Then the problem. Yeah, you have a question? Yes. So maybe I pronounced your name wrong.
That's good. Can you hear me?
Yes. Not very clear, but yes.
Can you go back to the previous slide? I was thinking about your test. Yeah, right. So I feel like you will lose quite a bit of power the way you set it up because so for example, let's say only one of the coefficients is non-zero and you have m is large. It's very likely that you will not be able to detect it. So I was wondering, so another way you could do this would be to take the max instead of taking the sum. So you look at the max of these scores. Of course, this will not going to give you chi-square m, but you end up with something a little more complicated. But perhaps you get a bit more power by working with the maximum. Does that make sense?
Sorry.
What I'm saying is that I'm comparing. I'm looking at the chi-square m and the chi-square. So let's say you only have the nulls does not hold. So you are in the alternative regime where only one of the coefficients is actually non-zero, but all of the other ones are zero. In that case, you went with right. So you get chi-square m minus 1 And then you have a signal, but on only one of the coefficients, but then you're not gonna be high enough, because your chi-square m large, m minus 1 will be, I feel like you will not have enough power to detect.
I see your point. I see your point. Actually, you catch a very good point. That's something I do not introduce here. So indeed, in statistical literature, this is called some diagnostics features of the smooth test. Indeed, they have a one-by-one, some like a one-by-one test of each of the parameters. Okay, so maybe you can consider each of the parameters is a average of Hg beta. So by the simple central limit theorem, maybe it's just a normal 0, 1, some under the null hypothesis. Okay, so you can indeed test each of these parameters under some careful settings. So you need to avoid some multiple testing problems, and also you need to take care of some interpretations of this theta j beta hat here. I think you are right. You catch a very good point. But here, this is your overall. This is like a overall test of whether or not your PM and G beta X they are fit each other or not, right? And you can do, I mean, like you said, maybe if one of them is very large and others are very small, then of course you can modify your M and you can modify your HG beta so that you only test one of them. This is one possible way. Or alternatively, you can perform some diagnostic tests that I said you perform one-by-one test for each of the theta j beta hat here, and maybe you will get clearer or more information based on this. Does this answer your question?
Is there literature on that? I mean, in that particular context, where, because of course, if you test it one by one, then you run into multiple testing, then you have to be careful with the way you do the correction for the multiple testing. What I was thinking is, without, you would take a max, you will go, but of course, if you take a max, then you will need to, just wondering whether people have looked at this in this particular context where they use they take the max of the statistics instead of the sum. Is there literature on that?
Right. This maximum actually, yes. Of course, there is. I think your point is very good, and maximum of it indeed it's called the Kolmogorov-Smirnov test statistics, and it's actually one of very famous test statistics that statisticians use. That's very good catch. And here I only introduce one of them. That's called a score statistic. That's one of the smooth test statistics.
So I think Yves is talking about basically I think in our own paper with Vinay, we call it with Vinay Margarita, we call it T-max or something. So it's not quite the Kolmogorov statistic, because the Kolmogorov statistic is not focusing just in a few directions determined by your H functions. What Yves is talking about is really just take the maximum of this coefficient squared or in absolute value or something, which is what we actually covered also in our paper. So in some sense, like, it's not necessarily true that you lose power with this test statistic taken as the sum of the squares. It really depends on the alternative, but it's a good point that is worth having both the maximum and the sum of the squares or whatever else. Underneath these test statistics, there is a empirical process. So in principle, you can take any functional of that empirical process and will give you a new test statistic. But yeah, so, as in goodness of fate, we have Kolmogorov-Smirnov, Craver-Moore-Mises, Anderson-Darling, and each detects some type of alternatives. Same problem here. I don't know if that helps.
Yeah, that helps. Yeah, thank you. That helps.
Yeah. Right. So indeed, we can have a bunch of test statistics, and each of them have some powers towards some alternative models. Right. So that's an idea. And of course, the case statistic that we have in our paper is for some scenarios, and the score statistic here for other general scenarios. Yeah, very good. Yeah. Now let's go to our real data examples, and we introduce that here indeed our task is to for the detection of the emission lines. Okay, we want to say if the spectral lines exists during the increase of soft flux, then we will think, okay, it support our opinion of the intrinsic synergy in soft thermal emission lines component. Otherwise, it supports the other scenario. But the problem is that our data set actually have some high background, high instrumental background. This is data set we use, and it meets some high instrumental background problems. Okay. And to solve this, actually, indeed, we already introduced enough tools for us to solve this problem. And for the first step, what we do is we perform the smooth test to the background model here. In our case, it can be a uniform distribution, it can be a uniform model, or some previous background models that you believe, you trust. And we fit this background model using the background only data. The data set only contains the background model. And if the test gets rejected, we will use the smooth estimator as our corrected background distributions. And of course, if your test gets accepted, maybe you will see the p-value if it's around 0.1 or 0.2, some very, very low p-values. You can change your M or change your basis functions to say whether or not there are some other kind of corrections. But if your p-value is very, very large, then maybe your background model so far is good enough. Okay. And for the second step, we will perform the smooth test using our corrected background models. And using these corrected background models, we will also use the data that potentially containing our emission lines. Okay, and if the test gets rejected, we can claim, okay, there exists such emission lines so that we can get the origins of that variabilities properties. Otherwise, we will set some upper limits on the intensities of expected signals. This is something that we haven't introduced, and I'm not gonna introduce in this talk, but that's how we do it in our previous case. Okay. Okay. So beforehand, we introduced a scenario that the test statistics is based on M is given and the beta is known. Okay. So in the next few minutes, my talk will focus on what if beta is unknown and what if M is not given. How do we solve this problem? And let's think of why under what circumstances M can be given and beta is known. Okay. So if beta is known, it means that we are testing a specific distribution function. For example, if your beta, if your J is a normal distribution and your beta is 0, 1, you are testing a specific standard normal distribution. Okay, and if beta is unknown, you are testing a family of a normal family of distribution functions. You have unknown mean and unknown variance. Maybe sometimes you standardize your data and you think you have mean 0, variance 1, so you can just test normal 0, 1, but maybe in general, you want to test a family of such distributions. Okay, and M here is given. It means that maybe your astrophysicists, they have more sense of interpreting your results. Maybe if your model gets rejected, you will have a sense that which direction it can deviate. Okay, which way it can go little bit different for your compare with your original postulated models, so that you can give a M, we can give a correct sense of basis functions. So otherwise, with statisticians also provide you a way for if beta is unknown, if M is unknown, how should we solve this problem? Okay. Okay, so for solve the problems of beta is unknown, so we need a little bit manipulations. Maybe you can think of why we do not just obtain an estimate of beta, maybe MLE or some method of moment estimator and plug in it. And is this fine? Or do we meet some problems? The main idea is yes, this is a method, but we need to handle it a little bit. Okay. So, here we let U beta to be the score function of the postulated distribution J beta. So it's a derivative of the beta, derivative of the log of the density with respect to beta. Okay. And the upper gamma beta is a Fisher information matrix. Then with the normalized score functions B beta, it's defined in this way. So it's just a standardized U beta, so that your B beta will have mean 0 and standard unit variant covariance matrix. Then we define the efficient scored functions tilde HJ beta as your HJ beta minus the orthogonal projections of HJ beta onto the space of B beta. Okay, and here is what you get. And these efficient score functions because when beta is unknown, okay, your HJ beta, it represents the directions. It represents the m-dimensional subspace that you have high powers. And if beta is unknown, this subspace actually contains some information about the about this score functions U beta. Okay, so we want to exclude this kind of information and to make it exclusively for your alternative models. That's why we perform this efficient score functions to make after this orthogonalization, your tilde H beta will only exclusively relevant for the alternative hypothesis. And otherwise, if you use HJ beta, it will convolve with some information about this betas, unknown betas, the score functions. Okay. Okay. So then we introduce here our generalized score statistics. We suppose beta hat n to be the MLE of beta, and we define our V hat as a vector of this VJNs here. And VJN is defined here. Indeed, it's some in statistics we called it a functional parametric empirical process, but here we just think of it's a summation, okay, for simplicity. So it's a vector of these summations, and our generalized score statistics is defined as this way, okay. And where this V is defined above, and this sigma V hat is a covariance matrix of V hat, and each of its elements is defined as this. Okay. And unfortunately, this sigma is not full rank, so we have to take a generalized inverse here. And we see that under the null hypothesis and as n goes to infinity, this Tm converging distribution to a chi-square R distribution, where this R is a rank of sigma we have. And this result actually can be extended for any root n consistent estimator. So it doesn't have to be the MLE. It can be your method of moment estimators or other method estimators, as long as it's a root n consistent estimators. In case you're not familiar with what is a root n consistent estimator, here is a definition. So your estimator beta hat n, okay, it minus the true density beta times square root n. It should be big OP1. Okay.
Xiangyu, a quick question. So what determines the rank of sigma v?
Sorry, say it again.
What determines the rank of sigma v hat?
Sigma V hat. What's a determinant?
No. What determines the rank? How you have this this score statistic going as chi sub r squared, but how do you know what r should be?
Right. That's a good question. So that's about you need to write this down a little bit, write this explicitly a little bit. After all, if you consider this tilde h is what we defined above, it's what we define here. Indeed, it should be a p times p is a dimension of your score functions. It's a number of your parameters p. This is p, and j is your number of m's. So basically you have P and M. You need to compare M and P. Usually M should be greater than P, so that if your M is greater than P and under the conditions that you are considering MLE, this should have rank M minus P. Okay, it's like that's a scenario. But if you consider
I was trying to figure out how that connects to the degrees of freedom, but okay. So that's
right. So if you consider some more general consistent estimator, so its degree of freedom is gets more complicated. So that's why we say it very general here. Okay, so so what we solve the problem that if we want to test a postulated family of distributions, and here we saw what if we do not have an idea of what this M could be. Okay, so remember we know that the power of the test, the power of our test actually depends on how well the true distribution is approximated by this M-dimensional smooth models. Okay, so because if your smooth model is very even though it uses M dimensions, it takes a smooth form. You make a truncations of the expansions, right? That's your smooth model. If you do this truncation and your smooth model is still very close to the true distribution, then your test only use this M parameters, it can get a very good test. Okay, you will not lose many powers. On the other hand, if you make this truncation and it cannot well represent your true model, then when you perform the test, you will lose a lot of the power, because many of the deviations that has some larger, for example, it has some deviations at the order of M+2. Okay, you cannot detect it, so that you will lose a lot of power. So that's why we say that the power of test depends on how well the true model is approximated by this M-dimensional smooth model. Okay, and the determinant of this M from this thinking can be seen as a model selection problem to find the best non-parametric density estimate of the true distribution. Okay, so we try to find the M that can provide a good estimations of the true distribution. Okay. For instance, the Colin Baker and Lavina, this paper in 1997, they based on they minimize so-called integral mean square error. That's one criteria about how do we say the best non-parametric density estimates. Okay, and they propose the following BIC type of criteria. Specifically, what they do is they first choose a large enough value of upper bound of its order. For example, it's 10. Okay, this is the upper bound of your order, and then we obtain the estimates. Here for simplicity we say it's MLE, but in general it can be any square root n consistent estimators of beta, and then we calculate our process VJN tilde HJ beta head. Okay, and finally we choose the smallest M that maximize our BIC criteria. Indeed, this is not exactly BIC, it's a BIC type of criteria. It's a sum of our process squares minus M log n. Okay, so that's how we perform the selections of this order M. Okay. Okay, so if we perform this model selection criteria, this order selection criteria, indeed we can meet some problems if we use the same set of data to perform the order selection, data selection, model selection, and we use the same set of data to perform our tests or to perform our inferences. Because under this scenario, your test statistic will no longer be this Tm. Okay, it will be the Tm times the indicator function that your selection criteria selects the order M. Okay, so your statistic will not be original one, and your limiting distribution will not be exactly this chi-square-R distribution. So that's a potential problems of this order selection criteria. In statistic literature, it's called the post-selection inference issues, and we see that the limiting distribution of the test statistics will be strongly affected by this additional source of variability associated with that selection process. Okay, there are several ways for tackling this. Maybe we can consider data splitting. That's a very simple way. We can just split our model selection and our inference steps, our test steps. Okay, this is one way we can do it. Another way is a suitable post-selection adjustment for the p-values. So maybe we can perform some Bonferroni adjustments, and it's very simple, it's very fast, but it can be conservative. It's not accurate. Okay, and this data splitting also have problems. It needs some extra sample size for you to perform model selection, and another data set for you to perform inference. And if you do not have enough data sets, that would be a problem. Okay. Okay. Sorry. Why? The bootstrap. On the other way, it allows for the selection process to be repeated within your bootstrap replicate, right? So that within your bootstrap, within your bootstrap replicate, you still have your test statistics times indicator function, and this will mimic your distribution functions of your test statistics. So this is a viable way. Okay, but bootstrap will not be conservative. It's an exact estimate of your p-values of your confidence interval, so on and so forth. So and it do not need that extra sample sizes. So bootstrap can solve these problems, but bootstrap can meet the problems of computational heavily computation problems. Okay, and this is how we solve the post-selection inference problems. And even we do not select the order m, if we are given some if someone give us a m, okay, our generalized score statistic Tm, okay, this Tm, so here what we introduce the generalized score statistic Tm here, it already has some problems, because here the result we prove is as n goes to infinity, we have a limiting distribution here, right? But indeed, some simulation results shows that, for example, the CLAR 2000, they demonstrate that the sample size as large as 10,000 are needed in testing a normal distribution, a very easy distribution, normal distribution, to achieve a good approximation to the chi-square-R distribution. Okay, so that sample size is too large in practice, so we cannot afford this, right? So that's a problem. Therefore, in practice, the p-values and the critical values, both of these are recommended to be determined using the parametric bootstrap procedures. However, as we said, and also the parametric bootstrap procedure can handle this post-selection inference problems. So it seems a desirable way to solve both of the post-selection inference problem and this slow convergence problems. Okay. One thing we need to mention is that when m is given and beta is known, under these scenarios, you do not have to perform the parametric bootstrap. But when either of them, when you either need to estimate your beta or you need some model selections, parametric bootstrap is preferred. Okay. However, the parametric bootstrap procedures can be computationally inefficient due to the complexity involved in because for the bootstrap, you need to sampling from the postulated distributions, right? If your postulated distribution is very complicated, like what we need to, I think another of our project is some stochastic gravitational wave background models. So that model is very complicated. It's very difficult to sampling from it. And sometimes it's even very difficult to get your likelihood or score functions evaluations. This is a problem. And also, if you contain the unknown parameters, you need to estimate their parameters and test statistics. That's also a problem. So all of these three problems can make your parametric bootstrap procedures very computationally inefficient and makes your whole procedure infeasible. And we propose solutions for these scenarios. The first thing we propose is so-called the projected parametric bootstrap. And this is to help the third scenarios. Okay, if we only have the third scenario, if only the parameters is hard to estimate, what we prove is that indeed you do not need to perform the parameter estimation within each of your bootstrap. Okay, so specifically, we show that, okay, if we see the parametric bootstrap samples is from the J beta hat n, and their samples are denoted as x1 bolt up to x1n bolt. So those are the samples from our J beta hat n from our parametric bootstrap procedures. And we let beta hat bolt be the parameter estimated based on the bootstrap samples. And this is what we learned in the regular bootstrap procedures. And what we have proven is that the process, okay, the process that uses the bootstrap samples and use bootstrap samples to estimate the parameters. Okay, you can see here we use bootstrap samples and we use the parameters that's based on these bootstrap samples. Okay, this one is asymptotically equivalent to the if we use bootstrap samples and we use our original estimates of the using the original samples, the parameters estimates of using original samples, they will be asymptotically the same. Okay, therefore therefore the test statistics that are based on these processes, for example, we take a sum of square of it or some others, are continuous functionals of them will have the same limiting distribution. Okay, so indeed this what we prove here is relies on very tiny assumptions. Okay, so we only require that the tilde hj beta here is continuously differentiable. That's very simple conditions, and also we require the components of each gradient of tilde hj beta are bounded by a integrable function mx. So this is also a reasonable assumptions. Then our results proves that for any root n estimators, it doesn't have to be the MLE. We will have our process, and the process based on the bootstrap samples and the process using the original samples. Their difference is only a small error term, and this error, the supremum of this error term converge in probability to 0. Okay, so it's consistent. It's consistent from very well. And if we further assume some regularity conditions by Babu and Rao 2004 and other conditions, then we can see that whether or not we use bootstrap samples and the original estimates of beta, or we use bootstrap samples and we use bootstrap estimates of the parameters, both of them will retrieve the distribution that we want. Okay, so that's a result that we prove. That's the first result we prove. Okay, then we still have two more questions that we want to solve, right? We maybe not only being efficient in the re-estimations of your parameters, your MLEs, but it can also be difficult to generate the samples, or it cannot easily evaluate its likelihood or score functions, right? You still have these two problems. And now we utilize a theory that in empirical process theory by some probabilists, they introduce some transformation that's called Caramelized 2 transformation, and it can help us solve this problem. Okay, so we will not go over it because it will be too technical. I will give you a reference and tell you what's the main idea of this. The main idea of this K2 transformation is we can produce some new K2 transformed test statistics whose limiting distribution under the very complicated postulated distribution is the same as some test statistics under a very simple reference distribution. Okay, why this is very useful, because when you have these results and you can perform a parametric bootstrap by sampling from this simple reference distribution and generate some test statistic, and it will have the same latent distributions as this test statistic under this complicated postulated distribution. So that for your inference, for your performing a test, you only need to calculate that complicated test statistic once, and you can simulate from the simple reference distribution and calculate that test statistic. Okay. And moreover, this method achieves so-called asymptotically distribution freeness. In practice, it can help us because when you try to test several hypothesis distributions, you only need to perform the simulation once rather than 3 or 4. If you are testing 3 models, maybe you want to test 3. You want to perform the simulation 3 times. But here, when we test this 3 hypothesis models, we only need to perform the simulation once, so that it also be computationally very efficient. Okay, so that's the idea of the K2 transformation. I will show you a reference to this method afterwards, but it's in the context of the goodness or classical goodness of fit test. But the idea is almost exactly the same with the smooth test. Okay, and extensions of the current work. So I think that's the last page of the talk I want to say today. So many of the real world problems in physics, astronomy, or some other areas, most of them depends on the bin data. So in our future work, we will extend all the methods described to address the bin data regime, and the modeling framework will incorporate the current work by Sarah and Kamalat. Okay, and for the K2 transformations, if you want to know more, I will refer you to read Sarah this paper for the goodness of fit test for the multivariate data, and it's published on PRD paper. And if you want to know more about smooth tests, if it's here this paper explains more about the smooth tests, and here this paper Sarah, I, and Winnie, and Margarita, this paper introduced how we apply our smooth tests in the literature of detecting line emissions under high background. Okay. Okay, so that's all I want to talk for today. Any question?
Hey, thank you, Xiangyu. It's a very impressive bit of work. Are there any questions? I don't see any hands or anyone speaking up. Let's see. So the one question that I have is, so this K2, what do you call them?
Yeah, K2
transformations. I mean, so we didn't actually use that in our work, right? In the
right.
For the RT crew.
Yeah.
So would that have what kind of change would that have produced in the results, if any?
Mainly it's a compute. Because our setting is like M is kind of given, and we are testing on some for some distributions that do not need to estimate the beta, so that our I think our let me see. Yeah, so I think mainly it will not change our main results, because K2, after all, it's a computational method. Okay, it can faster your parametric bootstrap procedures. And for our project, our beta need not to be estimated, and our M is even though it's use model selections, but we use what we use there is some post-selection adjustment for the p-values, so that we do not have the computational problems, and but the result we get can be very conservative. So maybe if we want in the future, we can perform some parametric bootstrap procedures to make our p-values to be more accurate, okay? And this may change some of our results. And I mean, if we use a parametric bootstrap, so we of course we need some K2 transformation to increase its speed if the model is complicated.
I mean, what sort of magnitude of correction do you think there would be? I mean, what we were after were, I mean, in most cases we didn't detect any of the lines that we were after.
Right. So I think when we do that project, we indeed tried the parametric bootstrap, okay, and we do not get very significant results, even though we use parametric bootstrap. Right.
So can I say something?
Sure.
It will actually not change anything, and it's not even relevant to the project we've been
Okay, all right.
in the sense that so it will not change anything because we calibrated our background using the smooth test. But then to detect the lines, we just use the likelihood ratio test. So nothing changes there. What is going to change is
we use likelihood ratio test to perform this upper limits, right? So
yeah, and also to give p-values for the detection of the lines.
Right.
So the smooth tests were actually used just in the preliminary phase where you wanted to check if the uniform background was reasonable for the reasons that we were considering, or if you needed to update it. But now say if you are in a more complex situation where the background is not a uniform, or if you want to test a model, like say, now we are working on some model testing for angular power spectral model. So you have, and these are like, it's far from a uniform, it's like several lines of code with parameters to be estimated. Yeah. So if you are in that sort of situation and you want to implement this smooth test, the parameter bootstrap might be extremely time consuming. And so the K2 transform will help there, basically, because then you can check if your background is good or not in an efficient way without running all the bootstrap simulation for a very complex model.
Okay.
I saw another people have a question.
Neta, I think I had a hand up.
Yeah, I have a question. Thanks for your talk. It was nice to see all the details. But I'm wondering if I want to use this, do you have actually the code which can be run, or you have to develop the method specifically for the application?
Right.
Of data in hand.
Very, very good question. So I'm not sure, do you use R or Python? In R, we have some code. I mean, we have some...
there could be R and could be Python. R is okay. Just thinking, yeah.
Right. We have packages in R, so that's totally
okay. Yeah. All right. So one can take a package in R. And what about Python?
Indeed, I write Python packages for this, but it's not that robust. So I maybe it's not that robust. I wrote it several years ago, but yeah.
Yeah. Okay. Yeah, just interested in in applications, because many astronomers who would like to use the method, they typically say, okay, so how do I use it? And they look for the tool, right? So this is where, if they understand what this can be applied to, then they want to use it. If we have a data in hand, like in the case of the problem with this low counts spectrum in Chandra, you have several possibilities, several similar problems. I mean, many similar problems in astronomy, and this could be applied to. So yeah, thanks. Thank you.
Yeah, thank you. Sure.
Margaret, I think, has a question.
No, it's just a comment on our paper. We did detect a potentially very important line, right?
Yeah,
in Arctic-Crew.
Yes.
That is quite an important and was not seen before.
Yeah, which is still not identified, honestly.
Right, but potentially very important, and it's in the paper. So
Yeah.
it's a very powerful method, given the data. You know,
Given the data. Yeah.
maybe next time you show people the spectrum, so see what your model, what your approach is dealing with. So it's very impressive. Very impressive.
Yeah. Just to bring everyone else up to speed, what that was there is evidence for photoionized lines in the spectrum, and at least that's what we believe. We could be wrong. We'll need better data, so we're hoping for CRISM. We'll see what happens. All right, Axel.
Yeah, thank you. I think you've not really talked about the choice of the basis functions that you use, right, to expand. And my question would be like, okay, what kind of basis functions did you use, and how does your result depend on the choice?
Oh, right. That's a good question. So, of course, it depends on the questions we have on hand. So in our case, we use Shifty Legendre polynomials. So they are just polynomials, okay? But if you believe your true model is some it's cosine basis, it's sim basis, you can use a cosine basis, sim basis, okay? But for our project, we believe if it get directed, if it needs some corrections, it should be some polynomials. So that's why we use a Shifty Legendre polynomials as our basis. Okay.
Yeah, thank you.
Can you go actually to the, I think slide 3, if I in my notes is signed correctly. There is actually a reason why you want to use, because shifted Legendre polynomial, so you take the Legendre polynomial, you place them on 0, 1, is what you want to use when you want to test for uniformity. And so if you see the structure of that he has in equation 2, you're taking your GB evaluated text, so CDF of the model that you're testing. And if the model that you're testing is correct, is uniform, G beta of X. So in this, indeed, is if you frame it this way, you're basically doing a test for uniformity, and therefore your natural choice for the psi j's are the shifted Legendre polynomials. But in principle, you can pick any orthonormal basis which is orthonormal with respect to this G beta, effectively. But with this transformation, Alex, I don't know if you're a statistician or astronomer, so but if you are an astronomer, this is this transformation GBX is a very well-known transformation called probability integral transform, and really test for goodness of fit started from this transformation by Kolmogorov in 1933. So they say, okay, take this transformation. Now you have found something that is, if your model is correct, is uniform. So effectively, you're doing a test for uniformity.
Okay, thank you.
Any other question?
Let's see, I don't see any hands up or people having questions. So as I warned you, Xiangyu, I said prepare for 20 minutes, and it's become an hour. So it's so thank you again. I just want to let everyone know we have another stat heavy talk next week. This is about the C statistic. This will be a double header by Yang Chen of Michigan and Max Bonamente of Alabama, Huntsville. So I guess we'll talk then. See you all then. So
Thank you, Hans.
Thank you.
Thank you. Very, very nice again,
Bye-bye.
Xiangyu.
Thanks, bye.
Stop recording.